talk about illustrative rendering, okay, which is basically the last lecture. Sorry, I have to drink something. Which is basically the last lecture in this volume rendering scientific visualization series. So basically, what this is all about is, can I move this to another place? I guess. Wow, cool. Okay. Can I make it horizontal? No, can't make that. Okay, so doesn't like to be completely compressed. Okay, so that's about, oh. Okay, this goes back to the top. Okay, so we'll let with this. Man, why does it have to be so? It really doesn't like to be ignored. So let's talk about this. So basically, this is about illustrative rendering, which is also often called non-photorealistic rendering. Okay, and we'll use these terms interchangeably. Like back then, when this became big in volume rendering, people called it non-photorealistic rendering. Then some some purists said, well, this is not good to have a non-photorealistic render because it doesn't tell me the truth. So they called it illustrative rendering instead. You know, illustrative is always good, right? You illustrate something, it's not a bad thing. Non-photorealistic means like you're occluding something, right? Maybe, and then suspicious people think that you may not be seeing everything that you should be seeing. So it's called illustrative rendering, is the politically correct term to this. So NPR, or illustrative or non-photorealistic rendering. So basically, when you have this photorealistic rendering, basically all you see is basically what the photo will give you, right? You know, but if the photo gives it in the wrong way, then you basically have to see that as well. So, but if you do illustrative rendering, you try to be an artist and suppress certain things that you may not think that you think are not important, and emphasize things that you think are important. So the kind of like, you know, the early painters, they painted things as they were, and then came the, you know, the more surrealistic renderers like Renoir and things like this, people like this who painted the world more abstractly, right? Or Picasso or something like these kind of people, Dali. Because the camera was invented, so everyone could already make pictures with a camera, so they had to make a difference, right? So they made things in ways that a camera couldn't make, like illustrative ways. So this is basically the, you know, Dali or Picasso or Renoir or these kind of people, they have this illustrative perception of the world. So for example, if you want to show a computer mouse, right, it's here on the left. Okay, like just this I could just suppress this. Okay, so when you have this mouse here, this is a photorealistic mouse. But if you want to see how a mouse functions, you can do the technical drawing. But then the technical drawing doesn't really give you any idea like what the mouse actually looked like, right? So basically these are two alternative views, but you can't really map them together. So some people, if you go out and look around on the internet, you can buy this mouse that looks like transparent. So you can actually see inside the mouse from the outside, you know, so you can see the microchip here and how the mouse buttons connect to some spring. You know, you can see all this stuff. But still, you know, some things are just still there because you still need to have all the parts, right? So some things you may want to see behind the integrated circuit, you may want to see behind these buttons, but you can't because the buttons are not transparent. So what you can do instead is you can make this illustrative for transparent rendering. So it's a computer graphics rendering. You can do all you want, right? If you have the description of the parts, you can emphasize certain parts, certain areas of certain objects inside the mouse, and you can de-emphasize others, right? And create this sort of picture where you can clearly understand there's like this lever here, and then there's this mouse button is connected, and here's the circuits. You know, so you get like a good idea what this mouse looks like. Of course, you can rotate it on the screen if you like. So this is basically this is non-photorealistic. This is still photorealistic, but now transparent. Here it's transparent, and here it's illustrative and transparent. You can't really buy a mouse like this because it doesn't have buttons, but you can understand what the mouse works, right? So basically this has been discovered, this kind of idea was like done by illustrative artists, like this guy Frank Netter, 1960, died like 30 years ago. He was called the medicine's Michelangelo because he basically would go and take cadavers and study them, what they look like, and then create pictures that would be illustrations of this human body, right? With like invisible things now made visible by painting. Okay, so if so here you can see the lungs and and so on, and here you can see the veins, and then here you can see the other things. So basically, you basically can superimpose the vasculature and things like this onto the body, and then understand how it sort of works in the context of the human body, right? So that's pretty good. But so you had to actually paint that, right? So that's why this guy did every day. He would like go and paint things, and then put it in a book, and that's it, right? But you couldn't really change it, right? You had to, like, if you want to see like you want to see the arteries instead of the veins, you would have to flip to the next page and look for that, right? If you want to see the muscles instead, you would have to flip to another page. If you want to see the gastric system, you would have to flip to another page. So this basically was all like painted, and you couldn't really change it without flipping a page. But this was really the first attempt to really make things more visible to observers, right? Without having to go and actually cut someone open and look at, right? Which you could never really do like this, So this was like illustrative rendering. So I remember, this was kind of the time when I was a PhD student and worked in volume rendering, and I was really thinking, volume rendering should be able to do something like this, right? Because you have all the volumetric data already, right? You can just use transfer functions and shading and opacity transfer functions and so on, and then a little bit of artistic rendering effects to make something like this, right? So, and I'll show you some examples later on that you actually can do this. So basically, just the definition what photorealistic, non-photorealistic rendering is, right? It's like a photorealistic depiction captures the exact appearance of the object, which can be a limiting paradigm. So now that's why you want to have non-photorealistic rendering, because you have freedom, complete freedom. You can basically differentiate salient features and suppress other things, and sort of really quickly sort of guide the user to the object that you want him to see, and then de-emphasize other things that are not relevant by this non-photorealistic depiction. And they also you can also use multiple styles, right? You can make things more interesting by changing the style, right? If you want to use a more impressionist render style, or you can use more colorful style, or more enhance the edges more. You can put points or pointillist style. You can do all this stuff, right? Now really the sky is the limit, right? All you have to do is like program the computer in such a way that it can make the picture. And we'll see some examples of this later on. You can also make a mood, right? You can sort of show like you can make things more dark or more bright, and then sort of guide the user in basically understanding what you meant when you made that picture. Okay, so this all goes back to Tufte's visualization rules. Like Tufte, we heard a little bit about him, but we'll hear more about him later on. He's at the Tufte. Is this guy who really was one of the fathers in visualization, who really put down these very ground rules here. For example, make all visual distinctions as subtle as possible but clear and effective, right? To really focus on the substance of a picture and then make that clear and effective, and disregard everything else, like basically maximize the data ink and minimize the non-data ink. Like focus on what you want to see and reduce everything else to not dark, right? Hide the data which doesn't make a difference in what you're trying to depict, minimize the clutter, and separate the figure and the background, right? These are all very important concepts that can guide your non-photorealistic rendering efforts, right? So minimize clutter, try to really make it very clear, separate the foreground and the background, hide things that you don't want the user to really see, or that you don't want the user to be confused by, maximize the data ink and minimize the data ink. All of these things are basically Tufte's ground rules. And we'll get to this again when we come later on, when we talk about the information visualization. You know, we have more on this, but for now, this is basically the concept of illustrative rendering. So if you have any question, you know, you can definitely ask. There's a chat window, we can use it. So feel free to ask any questions. Okay, so I'll every once in a while I'll go to this chat window and then check out if there's anybody asking something, and then I'll try to address it. Okay, so feel free to interact. Okay, it's enabled. Okay, so let's go back to this lecture. So basically, one very basic concept is contours and outlines. Okay, so a contour is a really good way to quickly get an idea of what an object looks like, because edges are usually seen. You know, we've talked about the vision system. Edges are usually seen what you see first, right? So if you want to become a good non-realistic illustrative renderer, then what you want to do is emphasize the edges first, because this is the most salient part of the object, right? So what you have to do, basically, you have to compute an edge map. So let's assume you have a computer graphics model like this, which if you just rendered it with regular rendering, it would look like this. But what really the edges are, they are discontinuities, right? Here's an edge that basically, here's object and here's background. Here's another edge, there is object. Here's a plane like this, and there's another plane like this, but they're orthogonal. So there's a discontinuity in the plane orientation. And there's there's another discontinuity in this crease, right? There's like a plane here and another plane here, and a polygon here and a polygon here, and then there's a discontinuity. So all you really have to do is you have to find these discontinuities, okay? So all you really have to do is find the normal maps. So this basically, you know, this is the normal vector points outward. This is where the normal vector points upward. Here's the normal vector point upward. Here's the normal vector points to the right. And you can't see the ones that point to the left because everything that points to the left is occluded by the viewpoint. Okay, so basically all you really need to do is color these polygons by the orientation of the normal vector. Here it's very simple. There's really only, you know, so many directions, and then just figure out where the normal vector changes. Just find out, okay, here the normal vector changes orientation, goes from here to here. And then whenever the normal vector changes orientation, you make a black dot. You know, make a black dot there. And then you immediately can see the edges, right? They immediately come out, right? Here I only show where it's only shown where it goes from object to non-object, right? It's like object here. This is basically the Z buffer, right? Where the depth goes from object to infinity. This is the normal. This is the edge map that comes from this, right? Everywhere there's a black dot. When the object, and when it's an object and non-object, right? Like just ambient shading. Basically, there is a shading here, no shading here. This is here's when you normal map discontinuity, right? And then you bring them together and make this. So this is just a very simple way to just get a really good description, like what a sketch artist would make, right? Like on the, you know, oftentimes they draw things, you know, that you meet them on the fair or something like this, and they draw a quick sketch of your face, basically with pencil, right? Oftentimes that's what they do, right? They would like try to find discontinuities. They try to find discontinuities and draw a line at those, right? So discontinuously going from object to non-object, or when the normal vector changes. And that's basically what comes out. So here's like more complicated objects you can get from this. This is just when you use the depth map only. You just compute when things are there in clear, when near, and things are not there, and with just background is shown, then you get that. And here's the normal map, discontinuity map. Bring it together, so you have a really nice rendering of a statue, right? I mean, it looks like, you know, pencil on paper drawing, right? It looks pretty good. You know, very simple method. All you have to do is test an array arrives, is it in the object or not? Draw a map, right? And then it's basically you look at the neighborhood, right? You basically look in this neighborhood, is this ray is the left neighborhood in the object and not, right? And then basically that's what you have to do to find. You have to basically inspect the local neighborhood and see if there is a change in the z value or a change in the normal vector. And whenever there's a change in normal vector, you make a black dot. Then you get this. So that's basically what they do. So then you can use this in volume rendering to make complex objects, right? For example, you can mix the outlines with volume rendering. So here I've shown like discontinuity is a normal vector, right? You can do these clear, nice edges and everything else is gone. And then you can show the inside in different color. For example, you can say, okay, this is the outside object. Everyone knows the engine, right? Because we talked about that engine in the volume rendering chapter. So basically here you can just change green for outside and red to the inside. Okay, and then you can mix it also together with like regular volume rendering and contour volume rendering right here as well for this valve here. Right, so anyway, so this is a very powerful technique that that sort of helps you to emphasize certain structures, you know, and you know, just use hidden, like here is basically hidden contours. You can draw them, just regular volume rendering, and inside the interior objects you draw them just in edge maps. So I have to. Everyone has to mute it. Okay, so okay, so let me see if there's any chats going on. No chats. Okay, so let's talk about silhouettes. Okay, let's go basic technique silhouettes. Okay, so silhouettes basically it's uses the dot product, and it every time the view vector and the normal vector is 0, then it's a silhouette point. Right? The silhouette basically is like the most extreme edge when you look at something from the front. Right? If this is the eye here, this is the normal vector. You basically just take the eye, right? You have eye vectors from everywhere to visualize the surface. And here, this ray here just grazes the object, right? Just here. This is basically where the normal vector points like this, upward, right? And the v vector is just grazing by. And so this dot product of normal vector and view vector is 0. And that basically just means there is a silhouette edge. Whenever you detect this, when you render a 3D object, when you detect there's a silhouette edge, you make that a black point, right? Just like before, right? So then you get basically something like this, right? So basically here, normal vector, you render this statue from the front, and here this is just the outer contour of it, right? The outer contour of it, and then you make just whenever the normal vector points perpendicular to your view vector, and then you just make that a black point, and then you know this basically connects automatically, right? And then you get a silhouette of this object. Of course, this doesn't look so good, right? Because it doesn't really capture the interior of the object at all. So that's why you want, you know, contours, right? So contours is a little more than a silhouette, you know. And then here's something called suggestive contours. That's even more than a silhouette. So let's go into what the contour point is. So a contour point basically is a point that Q is a contour point, right? So Q is a contour point. That's the one that is interior, right? This is a nearby view where, you know, this is the main view, and this is a contour point. And the suggestive contour point is P, when that's basically the point P is a point where the object makes an undulation, right? When the radial curvature is 0, like the curvature is 1 over curve radius, right? So here, when you look here, this point here is a radius, right? This curve has a radius. So there is somewhere a point here where you can define a circle around it, right? There's like a radius here inside, right? And you can sort of draw a circle around it. Of course, this center point changes as you move along, right? And here, this is an invert circle, right? So here, the center is here outside the object, right? Because it's contour, it warps around like this. So for here, this part here, you have an interior point, and this part here, you have an exterior point, and here you have an interior point again. And whenever this changes, right, whenever you change from the interior point to the exterior point and back, this is called inclination point. Okay, this is an inclination point. R is such an inclination point. And this is a suggestive contour, right? This is a suggestive contour. So this, this is basically that, right? And when you have detecting these, all you believe this basically is where the second derivative is 0. When the v dot n, the second derivative, this is not the derivative of v dot n, but when the v dot n changes. Like it's not going to 0, it's just have a minimum, and then it goes back up, right? It just has a minimum and then goes back up here. So the v dot n gets smaller, has a minimum here, and then goes back up, right? And this is where you want the suggestive contour to be drawn, okay? And then you get pictures like this, right? This is basically here, this sort of, this local minimum, that when it goes in and out again, right? That's where a suggestive contour would arise. Here also. So you get all of the wrinkles of a forehead, and you can also get at the eye, you can get these wrinkles in the eye, right? And, so that's why when it's really early in the morning, you look very wrinkly, or very late at night, you look very wrinkly, because the light shines in the wrong way, and it like really emphasizes these kind of contours. When the light comes straight from the front, you don't really see it that well, but when the red light comes sort of from the side, like in the morning or late night, you can see it a lot more, right? So we'll get to this in a second, right? So this basically suggestive contours, local minima and the curvature, local minima curvature. This makes things very expressive, right? Makes things very much look much better. So let's look more, right? This is like a suggestive contour. You can compute it in screen space, or you can put it in object space. Screen space, basically, you project all the normals in there and compute those local minima. But you better do this in the volume, directly in the 3D space. Then you'll get a much better rendition of it. Because otherwise, you get a lot of noise, right? Because when you project things, things become a little more inaccurate, right? Because there's round off errors and things. And here, when you do it in 3D, everything's a floating point. You can get things much clearer. So these hand here looks much better when you do these things in 3D. Just like what I wrote here, right? You just compute that in 3D. Main viewpoint, compute the local, the normal vector, and with the view vector, right? And figure out where the local derivative is, when the second derivative is 0 for that, right? But you have to look at basically, if you want to compute the derivative, you just have to look to the side a little bit and figure out what is the v dot n dot product doing, right? And if it's big on one side and big on the other side, there's a local minimum here. Then you can draw the black point. Okay, so basically that's so much, and then you can. So this is a volume rendering that does this. So here is basically suggestive contours. Is another suggestive contour. So things look really realistic, right? Kind of looks like almost like on a graveyard, right? When you dig out the head and look at it in the morning, right? It really looks very realistic. This looks really artificial, right? This is just a volume rendering. This is also volume rendering, right? Not that good, but here you can see the double chin of this guy here. You couldn't really see it well here, but you can really emphasize it here too, right? You can really, it looks very, very, expressionist, right? And that's really what it is. It's really, it both gives every little detail. Okay, and the ears, you can also see that it gives like a three-dimensional effect, although there is no 3D, but you can really see also an illustrative effect, because that's what usually artists do too, right? They basically make an extra dark line there where there is like this suggestive contour, right? And now you can basically use the computer to do the same thing. Okay. So these look really good, right? So just second derivative at high accuracy, you need to compute that, right? In volume rendering, you have to actually compute this from the volume data, right? You have to actually estimate that from interpolation. So before we learned about first derivatives to compute a normal vector, now you have to actually apply a second derivative filter, not just the central differencing method. Now you have to do the central difference of the central difference, right? Which is a higher order filter. You have to apply that. You need more support around, right? We didn't talk about in class how this higher order filter looks like. Usually it's basically a second derivative filter, and so that one you have to apply. So the next thing, which is illustrative, is this also quite old method from '96 by Victoria Interranti, which basically said how, she struggled with this area. This is like in 1996, so this is quite some while ago, right? 25 years ago almost. So basically, when you do semi-transparent volume rendering, right, you'll see this. This is a tumor, by the way, in a lung, and you want to basically, this was made for radiation treatment, right? But let's forget why it is for. The key is really to show how is the outside surface look like with respect to the inside, right? How can you bring out the dynamics, the geometry of the outside surface, when you do semi-transparent volume rendering, right? How can you do that? So what she did was she basically added these strokes along principal curvatures, right? These are principal curvature lines, that are around. So basically, these are the curvature. These are the lines that wrap around the surface, right? And you can detect them again with second derivative methods, right? So just and render them as strokes, and then all of a sudden you get a really good idea how that the surface really, that there's really like sort of a bulge, right? There's a bulge here and there's another bulge here, another bulge here. You can really get an idea what this outside surface looks like, and you can still see the inside surface as well, right? So it's not really occluded at all, right? Because these lines here, they don't really occlude the surface that much, right? You can still see what's inside. It's just sort of artistically rendered in a sparse way, right? So that really helps a lot, right? So that's basically another non-photorealistic rendering method, where you can do that. So this is a good method. Then another method is what's called hatching. Okay, hatching. So I don't know. I want to get rid of this. Okay, so hatching. So hatching essentially is a way to add illustrative effects based on the normal vector, based on a dot product of the light vector with a normal vector. Okay, similar to shading, Gouraud shading, the diffuse shading. Instead of using less or more, make it darker or not so dark, you pick from a set of textures, okay, which is called the tonal arc map, right? So when the normal vector is pointing away from the light source, from the view, then you pick a dark one, right, a very dense texture, and when the light vector is pointing with the normal vector, right, when the dot product is very high, you'll pick a texture that is much sparser. Okay, so now you have this kind of sparse texture here. And so that's basically, now you control the selection of these textures with the dot product of the light vector and the normal vector, right? And you can sort of get this very interesting painterly effect. It's very simple, right? Instead of just choosing instead of choosing modulating intensity, you figure out what texture you would choose, right? Which texture you would index. And since this changes very smoothly, right? This changes very smoothly, you're going to end up in the same texture for a while. So you're going to, let's say, a neighborhood of pixels here will have similar dot products of normal vector and light vector, right? And then they'll end up in a similar texture. And then as you go along, right, you'll go along in this texture as well, right? So you basically replicate this texture here. Then after a while, you're going to go into a texture that's a little less sparse or more sparse than here, right? And then you start moving from one texture to another. So everything is very smooth in terms of the change. And then, basically it starts moving from one texture to another, right? And then if it stays in the same texture, it just goes, as you go through here, it'll move through the texture as well. So you can get these sort of texturing effects, okay? So this is another kind of style. This is called the stippling style. Okay, instead of you have a texture with sort of which are stroke textures, you get a stipple texture. Okay, so this is like basically either you can randomize the points or not. If you can just use a randomization, or you can actually use a texture as a background, right? That you basically vary the density of the points depending on the illumination. Again, the dot product with the view vector and the normal vector and the light vector, or anything else you like to have, right? And then you can create these sort of pictures out of that, right? So it looks. And here's also mixed rendering style. Here you use pointillist texturing, and here you used more photorealistic rendering here, right? Although they have a little bit of pointillist rendering in there too. It's also quite old, like from 2007. So, but these are very interesting techniques to make things more interesting and really emphasize what you want to see. So basically, the emphasis here is definitely on this artery, right? And this is just a context, right? This is just a context. So you see, this is the lung or something, and then here, this is the heart, this is the artery, right? And then, you know, so you can really see what you want the user to look at, right? And where in what neighborhood it is, right? So that's basically what you can use a rendering style for. Try to point out the important from the non-important, but still show the context. Okay, basically just what artists do. This is what people did when they made these medical atlases. They did the same tricks, right? They used the same tricks, so now you just replicate it on a computer. Also notice here there's a contour line, hidden contour line, right? So you basically have to figure out what's behind, and then you only render the edges, right? You detect the silhouettes and then render the silhouettes by dashed lines. Yep, so that's what you do. So now the next part is highlighted edges, okay? Highlighted edges. So, okay. So, you know, so basically this is an observation, this from Gooch et al. They made the observation that, you know, when you look at a metal object like this, it always kind of looks like this, where these edges that are facing the viewer are white, and the edges that are not facing the viewer are dark, right? That's what it looks like, right? So it's like, and you can now take this knowledge, right, and incorporate it into the rendering engine, where you basically, whenever the view vector and the normal vector are both pointing at you, then you make that edge white, and when it's pointing away from you, like when the normal vector is pointing away from the view vector, you make it dark. Right? That's all you have to do. And then that's basically, you know, that's how you can render really impressive objects. Of course, there's also tone shading, and we'll talk about tone shading in a minute, you know, but we'll for now we'll focus on these edges, right? Color interior edges white, and the other ones that point away black, right? You can really create a nice sort of non-photorealistic effect. So let's talk about tone shading. Okay, tone shading again by Gooch et al. It's also again 98. So, but these are very effective ways to do these kind of things. So basically, this is a typical photorealistic image, like rendered by volume rendering, right? Isosurface volume rendering, right? This looks, you know, it looks good, but there's a few things that are really problematic. For example, the shading basically rendered everything here in black, right? You can't really see what is really there, right? Because everything is black, right? Like because the dot product of the light vector came from the top, right? And the surface normal pointed to the bottom, so the dot product was very small, and then basically there was not much intensity added to this particular surface, right? So it doesn't really look good, right? So instead, what they did, you know, you can, you know, you remove the diffuse shading, right? You know, if you don't like what the diffuse shading does, why not remove it? Okay, so here's without remove the diffuse shading. So now nothing's in the dark anymore. You add some edge effects, right? You highlight the edges, also keep the specular highlights. So this is what it looks like now. It's already non-photorealistic because real life bone, when you go to Natural History Museum, for example, looks like this if there's only one light source. Of course, when there's more light sources, then you can get more information, but then there's always one light source. Then that's what you get. And then if you remove the light effects, right, then you get this. But the problematic here now, you don't really see the shape anymore, right? It sort of looks like this plasticky kind of thing that doesn't have any shape information. So what you can do here instead, you can do edge lines and highlight better, and then try your best what you can do, but still dark areas are gone. So what you can do here instead, you can, instead of using shading when you have the dot product of the the dot product of the surface with the light vector, right? Instead of using this dot product to modify intensity, you can modify color, right? You can modify color. You basically, small dot product looks up blue and high dot product looks up red, and everything in between, right? Everything between. So this is called tone shading. Okay. So what you basically need is a color map like this. So here, for example, we went from pure blue to yellow. Okay. And here you went from pure black to the object color, right? And you add this. You can add this together. This is just really basically, you darken a little bit. This is just basically the color effect that you use, and then here, this is when you want to go from pure. This is what the original was, right? Then we go from black object color, right? This is and you want to make sure that dark things that are hidden become dark. And here you map blue onto those areas instead, right? And then you get sort of this combined final tone, okay? Then you get pictures like this, right? This is basically nothing like this. They're nothing but this, right? This is basically using this tone map and applying it to the rendering of this surface. Now you can really see, right? You can really see, instead of having a dark part here, now it's blue, right? And it's still the same light, right? It still basically still looks like this. There's still enough light there, but now you can see the shape changes. You see it by color degradation, right? Before, here you could see shape changes because it was dark and white. Here you couldn't see the shape changes because it was all white. And now you can see all white, but at the same time also shape changes by using different colors for different areas of the object, determined by the dot product of the normal vector and the light vector, right? So basically, this is basically both good things of. Basically, this is.
Sorry, I didn't quite catch that. Could you please repeat?
This is Siri. I hate this thing. So then. Okay, so then basically go in and sort of get the best of two worlds, right? Here you get the things out, you get the good out of smooth shading. At the same time, you get the best out of the contours, right? So basically both inside at the same time. That you control it by these colors. The sky's the limit, right? You can really use any type of color code here and any type here, right? You can just mix them together and then create very different sort of tone maps, right? You can go from, here is much more dark, right? And here it's a little more varied, right? So this is you can really change the mood very nicely just by using these swatches, right? Just by using these swatches. This all looks really good, right? This sort of looks like this one here, right? Here's more yellowish, right? You can just control it by using the right color ramps, and it's really simple to figure out, right? And then you can just map them together and create these interesting effects, So basically, this is you can weigh them together, right? You can weigh a little bit of tone shading and a little bit of of regular shading, right? You can mix them together so it's not as extreme as here, right? So you can make it just very subtle, right? And then. That's basically illustrative rendering, right? Because you're in full control what your object looks like. It's like an artistic kind of way to do this, simply controlled by creating the right ramp functions and the right weighting. How much do you want photorealistic and how much you want non-photorealistic, and you just weight them together. Basically, render two images and mix them together. Then you can get these kind of effects. Okay, so people have used this for volume visualization. So render the foot with tone shading, okay, or for vessels, you can look at it like this. These are like vessels shaded with tone shading. So another thing from Gooch et al. Is all in a book called Non-Photorealistic Rendering that you can buy, called Non-Photorealistic Rendering. It's a book you can get online, or you can probably get in a library. So they have a lot of these effects. Okay, these are just a few of them. Another one basically what Gooch, Amy and Bruce Gooch, they're a couple now at the University of Texas in University of Texas at College Station, I think. So I actually know them. So they just went around and observed. All you have to do is observe what occurs in real nature, and then try to simulate it on a computer, right? So here they observed that when you look at metal objects, there's oftentimes these sort of random sort of effects of there's like a very bright stripe, and then there's a dark stripe and a little less bright stripe. And all you will have to do is randomize this, right? And figure out, you want to okay, I make a white stripe here and I make a black stripe here, and just simulate this based on the curvature, based on where you are on the curve. And you just figure out what if you use a white pixel or a darker pixel, and then you get these sort of interesting effects right here too. Right, very clearly you can see it, right? Dark, bright. Just figure out, but just by where the normal vector and the view vector are, where the normal vector and the light vector are, pick a different intensity and make it very sharp, right? Randomize or make it very sharp, right? And you can get these very interesting effects out of it. Right, they can get this too. So now they mixed it together with tone shading, right? So once you have a nice toolbox, you can mix it, right? So here's just with the edge lines only, and here you add the tone shading again to it. So you make these very beautiful pictures that look like artwork, and they seem like they're hard to make, right? When you look at this and say, how did they do this? But it's very simple. Color maps, compute the dot products of those vectors, figure out where you go in those maps, randomize on the strips, on the white and black strips, right, and then done, right, and then mix together the original with the tone shading, and then you have a picture, right? It's just have a few sliders where you manipulate what you want to see, keep rendering this until you see something that you like, right? I'm sure they didn't compute this right away, right? I'm sure they tried very hard to figure out the right settings for these different ramps and so on, right? But then, they got it, right? So that's basically all you need to do is have a few sliders on your interface, a renderer there, and then different effects map to those sliders and change them, and then create these pictures on the fly, and then use them if you like, right? So here's another one. This is again tone shading, here's with background highlight, and here without it, right? Here it looks very diffuse, right? Here looks a little more plasticky. And here it's also these white strips are there, right? They are not there here, right? So it looks very, very cool, right? Very nice, just simple effects. So then back to volume rendering. So let me see if there's any questions in the chat. Don't know. Okay. Where was the chat again? Forgot. Okay, so let me see. Okay, there's a chat. Okay, Phil. So NPR rendering extensively used in designing graphic games. Oh yes, I'm sure. I'm sure there is graphic. I mean, I'm not a big gamer, so I can't really tell you. But these effects are very, very heavily used, right, to make things. Because with NPR, right, you can give it your own personal style, right? Because when you do regular rendering that follows the physical laws, everyone has these physical laws, and for everyone they're the same, right? But when you have a non-NPR renderer, and you can manipulate the appearance with these really simple, it's still simple physical laws that you use, right? It's just dot products and ramps, right? But now you can really figure out how much you're mixing together, right? It's basically like a music that you compose. And now you can give the game a particular look and feel, right? You can give the feel, you can give this feel here, and let's go back to this. You can say, I want my game to look more like this, or I want my game to look more like this, right? Or my game more like this, right? You can use these balls here, right, to guide it, right? I want to look my game more like reddish, or want to make it more like yellowish, right? And then I can make it anything you can do, right? Just by mixing them together, you can create very interesting effects. And then once you figured out how much contributions of each of these effects you'll have, you can render everything like that, right? You can also focus it, and this actually brings me to the next slide. You can focus your effects on certain areas, right? You can basically say the skull I want to render in a certain way, and the trachea and the skeleton I want to in a different way, right? So here, this is what Helwig Hauser and Markus Hartwiger did. They they rendered the skull in X-ray mode, and the trachea, where the food goes on, they rendered the maximum intensity projection, and the eyes did it with regular volume rendering, and the skin, like they made it with silhouette rendering, right? So mixing together, right, in new ways, you can really make things look very, very interesting. And if you have like your game characters running around like this, people will enjoy to play that game, right? Of course, you have to have the right mechanics to it too, but people will enjoy to have this game because it's visually interesting and surprising, right? And then that's basically what you can do. And the simple effects here, it's just the skin with silhouette. Remember, silhouette detect where the view vector and the normal vector is to 0, right? Render a black point, right? Silhouette down, right? Direct volume. All you need to know really is where is my skin, where is my eyes, and where is my skull. And that you can do by having another volume, for example, which is a tag volume, right? So the volume will, for every voxel, you have a tag that says what it is. So before you run a segmentation on it and say, okay, this voxel here is my skull voxel, and this voxel here is my tooth voxel, this voxel here is my trachea voxel, and this voxel here is my skeleton voxel, right? Then when you do the ray casting, you cast both volume at the same time, right? You cast the volume with the densities, and you cast the volume with the tags. Or you do it on the fly, right? You recognize the different parts on the fly. You can of course do that as well if it's simple, right? But you can also pop before and segment it. And then you basically where you are, right? You just say, okay, your ray has gone particular point. Then you'll decide, okay, I'm in the skull now. Okay, I'm gonna use X-ray. This particular ray point. I'm gonna when I sum up the ray points along the ray, I'm gonna use an X-ray function for it, right? When I'm in the trachea is, then I'm gonna maximum intensity projection basically. So basically, what you will do is you render each ray, let it go through the entire volume. For each sample, you decide how you want to render it. And then as you sum up the samples, you go from front to back. If you encounter maximum intensity projection sample, then you stop there, right? Or you figure out if it's the maximum if it's the maximum value along the ray. If it's an X-ray sample, you just sum it. If it's a shaded volume rendering sample, you compute the color first by shading and then adding it, right? So basically, that's what you do here, right? You traverse the volume, decide what rendering effect you want to use for this particular ray sample, and just keep the ray samples aligned front to back, and then traverse that whole sampling ray, depending, and decide how you're going to add it to the ray sum, depending what they are. If it's, and then you can compute this kind of volume. Okay, so yes, well, you can in games you can do the same thing. You can say I want to render the humans, I want to render them in a certain way, and I want to render the objects in a different way, and the background yet in a different way. You can do all that by tagging and keeping IDs of the object. Right? You can do that. So let me see if there's any more questions. Okay, sure, welcome. So let's go on. So now now we've learned a little bit about these different techniques in non-illustrative rendering. We learned about contour maps, and this is so basically, if you want, oftentimes Illustrator use this kind of technique, right, where they have an object that it sort of serves as a container object, right? Just an object that sort of tells you like where everything is and what it actually is. So in this case, if you only saw the vessels, right, which is your focus contact, you know, and they're usually emphasized to be, they're rendered at a very high fidelity style, right? You can really see every little detail. There's also nice color differentiation, so on. And those usually are the focus objects, because the viewer will see, wow, you know, my render really spent a lot of effort on this particular object. Therefore, I think it must probably be the most important one, right? And then basically this is the focus. And then you render a little bit the near focus object. These are the objects that are needed to understand what this actually is, right? So in this case, this is a lung, right? And this is sort of the surround of the lung. And this, you know, so this, you need this context so you know where these alveoli go, right? Where these lung vessels go, right? Where these, you know, where these go, right? So these are these alveoli. That's where basically where the oxygen comes along and then gets absorbed by the blood, right? So this is what happens when pneumonia, right, happens. Then there's a lot of water in there, right? And you know, things like the lung cancer also attacks this. So anyway, so now you're supposed to tell the person, okay, you must focus on these air ducts, right? And then I will show you what the lung looks like in sort of as a container, right, as a sort of surround. And you know, here is a little more. This is a context object. You know, this is a near focus object or context object, and here's the container object, right? And so you can really sort of, just by rendering, right? You just decide, because you have discovered what the different objects are. You have to make a tag volume beforehand, and whenever your ray meets a certain object, it decides, okay, I'm only rendering the silhouette because it's just a container object. Oh no, wait a minute, I'm going to render a little more color, you know, to the volume because it's a near focus object. Or I'm going to render it I'm going to really make it find the structure, overall structure. I'm going to really differentiate the surfaces, right? And that because it's a focus object. So here this is like a picture of this, right? There's the focus object, the context object is that one, near focus object is this here, right? It's like also rendered at high detail, but not transparent, right? And then here there's the container, right? Just by changing rendering style, you can really tell a story just by, you know, it's illustration, and you have all the tools, right? The only challenge really is to figure out what is what, right? And you can just do this either on the fly. You have to recognize by the density or what it is, and if you can't do that, you run a segmentation algorithm before and create a three-dimensional tag volume that tells you what voxel each voxel is. If it's a container or focus, if it's a rib cage, or if it's alveoli, or if it's a lung surface, or what it is, right? And then you can just render that, right? So this is essentially, you know, applied, you know, volume rendering. But you can do the same techniques. I don't have a picture for this, but you can also do it for scatter plots, for example. You can render a lot of points in areas where you want the user to look at, and only render very shaded, very, very smooth kind of point cloud around things where you don't want the user to look at, just as a context. But you can do that with I don't have a picture of this, but you know, you can do the same thing with information visualization, right? Some areas, like you can have a scatter plot. Wherever you want the user to look at, you have to show the individual points. And where you want the user just to get some context, you just render it by blurring the points around it, right? So it's just very, very sort of blurry look. And you can maybe give a color to that too. And if maybe the outside you don't even color, right? And you can do the same thing also for information visualization. So these techniques apply everywhere. Okay, so they can also change the rendering style. Okay, and we'll talk about this too. So what I want to, because we only have like 20 minutes left, so let's go, because I have a few more slides left here. So this is a very interesting work by Bruckner, Stefan Bruckner from the University of Vienna. So actually Vienna, University of Technology. So what they did here, when you look at this, can't you see like how nicely these vessels pop out, right? Here they don't really pop that much, but here, for example, here when you really look at it, the detail, they really pop out. You can really see that it's in front of the other, right? Here you don't really know that much, but here you can really see it. It's because they look like they render a little bit of a shadow on it, or basically what they have is a halo. So basically what they do is they render, when you volume render this particular vessel, let's look at the vessel, this particular vessel, when you look at it from the front, from the volume. So here this is shown like the rays are going through the vessel. So the rays are going from the front to the back, right? And when the rays are near the object, but when they go traverse the object itself, then they're gonna make the object color. And when they're just near the object, so you have to have a distance function there, right? You have to sort of have a distance field to that goes with the parts of the volume, right? You have to sort of figure out, is there, and then basically you render that, you imagine that there's like a black cloud around it, right? And whenever there's a black cloud around it, then what you render is of course black, and then you can see that, right? So here, this is basically a picture, right? But here when the ray came to the middle, it made it red, and then it just went by the neighborhood of this vessel here, and it rendered black, right? And then it couldn't really render the background, right? Because it's already opaque and black, right? So it's basically a vessel with an opaque black layer around it. And then when you render that together, then you're gonna see this sort of interesting effect that you have this black halo around it, right? And you can really clearly see that this is in front of the other, right? And this is like the hand rendered like this. Here's a flow volume. This is by Wenger and Lidlow, I think. So you can really make things look really, really 3D, right? It's just another rendering, but now you add this additional, effect to it, which is a halo, right? And then you can see things much clearer because you leave like a black cloud around it, right? And then all you really have to figure out, are you close to the neighborhood or not? And then you just make that object, make it red and make it black. And then make it very opaque. Then you can't see anything in the back, right? Actually, your object's always opaque, right? Here in this case, there's no semi-transparent object, right? It's either the object that you see or nothing, right? So that's basically the halo effect, right? So we make really good pictures, really nice pictures. Another interesting effect is this inconsistent shading. So let me see if there's any questions. Okay, no questions. So inconsistent shading. So also very interesting. Let me go to this picture here first. I don't know if you ever been to Utah and saw saw these canyons there. For example, Bryce Canyon is there. Okay, to see this Bryce Canyon, maybe you've seen it on pictures. To see this canyon like this, you have to get up very early in the morning. During the day, it doesn't look like this, but early in the morning, it looks like this, because this is when the sun is like still really low down, and what happens then? It basically, the sun rays are just sort of grazing the surface, right? They're not coming from the top down, right? They're actually coming from the side, right? So then, basically, what happens then here? It's also the same thing when you walk by a building in very early in the morning, right? You can see like small fissures in the building or small scale features, gaps. You can see all of these things much easier in the morning and or late or in the evening than during the day, right? Because rays are sort of going alongside these surfaces. They don't fall on them directly. They sort of go by them. They go by them like this, and then when the rays go by them, then they cannot go into the holes of the surface, right? If there's like a surface, but it's a little bit of an indentation, the ray can't see it, right? The ray cannot go into it, and then when you look at it from the front, that basically looks dark to you. So when you look at this golf ball, for example, right, the ray came from the side, right? The ray came from the side. And it only was able to illuminate this outside of the surface, outside of this hole, but couldn't illuminate the inside of this gap, inside of this pore. That's why you can see this 3D detail so well. Of course, you've never seen a golf ball like this. You know, you've never seen a golf ball like this. They always look like this, right? They never look like this, because this is computed by computer graphics using what's called inconsistent shading. So essentially what this inconsistent shading does, it everywhere along the golf ball, it made the light go right tangential to the surface, basically orthogonal to the normal, overall normal. Okay, so just think of it as a golf ball where you have rays going around it. You know, everywhere you look at it, the light comes always right from the side, right? Everywhere you go. So the ray, basically the light is inconsistent, right? For some areas it goes up and goes out, inside out, right? Some areas it goes by, and some areas it goes down, right? So the only computer graphics can do that, right? You cannot really create this with a regular light source, right? You can only simulate it. And if you simulate it, you can get really interesting renderings, right? So this is like consistent shading of a skull. This is inconsistent shading of the skull. And you can see a lot more. You can see the surface detail much easier than here, right? Here it looks like this sort of plasticky kind of look. Here you can really see the very, very fine detail, very, very small indentations. You can see it really nicely, right? You can see the gaps in the teeth very nicely. You can see behind here very nicely. See the joints very nicely. When you open it up, you can see every little crease in the skull, right? You couldn't see that anywhere else. So the way it works is like this, okay? So the way you would do it is like this. The first thing you do is, if these are your normal vectors, this is like just a part of the surface. This is the top here, this is the normal vectors, they will point like this. Then you take a smoothing function, okay? You're gonna smooth the normal vectors, you know, and in this small area here, they would all point the same way, right? It's basically the average normal vector of all of those normal vectors, you know, so this is the average normal vector, right? So everyone is a little bent to the average. This is bent here, this is bent here. Compute the average normal vector around in a moving way. And these now are your smooth normal vectors, okay? And then when you light this, you do this throughout the object, right? So your average normal vector will also change, right? For example, at this golf ball, average normal vector here will point like this, average normal vector here points outward, average normal vector points like this, and so on. But it's sort of a slowly changing normal vector, right? It doesn't really react anymore to those inside interior detail, right? The normal vector originally goes wildly everywhere around, right? Because it wants to represent every little detail. But the average normal vector just sort of presents the overall shape of the surface and not the detail, right? Basically, essentially just the curvature of the ball itself. It doesn't represent the interior detail of this golf ball. And then what you do, once you have this average normal vector, which really just represents the overall surface shape, then you orient the light vector as orthogonal to that average normal vector, right? Then you basically have this. So now you basically compute the light vector as you want it to arrive at this particular area of the object, okay? That of course changes depending on the average normal vector, but here it just points like this. And then to compute the actual shading, you take the real normal vector and compute the dot product, right? Take the real normal vector, compute dot product. So now what you have basically done is you computed the average normal vector that changes very smoothly over the object. But then for shading, you actually you oriented the light source perpendicular to it, because this gives you this nice Bryce Canyon effect, right? And then you change the lights, then you change the light source a little bit, you know, you change the dot product a little bit because you use the real normal vector, right? So now you get really small changes you get to capture really nicely, right? The normal vector just changes very small, and this is where the sensitivity is the largest, right? Because sensitivity is the largest when it's perpendicular and just not perpendicular, right? Because that's when the derivative gets, this is a sine function, right? The cosine function, that's when the derivative gets the largest, right? So then basically you get very rapid changes in illumination or very rapid changes in intensity. And then you can bring out these effects very nicely, right? So this is like inconsistent shading by Rysinkiewicz, And there was a paper, Sigarev paper, and later on Lee wrote another paper on the visualization conference. So it's a very nice way to really bring out these sort of features. So here's like inconsistent shading kind of pictures. Okay, well, you would say it looks inconsistent because it looks unnatural, right? Elephants never look like this, right? Or even statues of elephants never look like this. Even if you choose a light source, no matter where you put them, right? Even in a museum, it doesn't look like this, right? You can only really achieve this by computer graphics, right? Same thing with this Sumerian tablet, right? When you dig it out, when you look at it in the National System Museum, or when you look at it in an archaeology exhibit, it never looks like this, right? It never looks like this. It looks like this, right? You can never see all the features like this. But by tuning the normal vector and the light source perfectly, the light source direction in relation to the normal vector, local normal vector, if you tune it perfectly, then you can see the Sumerian tablet like this, right? And actually, but for Sumerian tablet, right, you don't even have a model, right? You have to first acquire the model. So what this Tom Malzbender did 10 years ago, he built a light dome. So he illuminated an object from different directions and took a camera and figured out where is the illumination best. Basically just illuminate from all directions, take a picture for each particular illumination. So if you have like 50 illumination directions, you have 50 pictures. And then you basically have a stack of 50 different pictures of the Sumerian tablet. And you always figure out, no matter where you are on the tablet, you figure out the best contrast, right? And then you can really bring it together, really can see things that you couldn't really see before, right? Actually, archaeologists could never figure out what the Sumerian tablet was all about until they used this kind of lighting technique. First acquisition with this light dome, and then lighting technique to really render it like this. Before, no one knew what could really decipher the Sumerian tablet. But once they had this kind of acquisition and then rendition, they could really see it very nicely. Okay, so that's basically, and then you can also create this figure of this David's head, right? So Michelangelo's head, right? So you can really see things very nicely. But of course, it's completely looks artificial, but by design, right? But you can bring out every detail in one picture. So which is the secret here, right? You don't have to look at multiple pictures to see every little detail. You can just look at it all at once in a single picture. So it's a really good, visualization technique, right? Because it summarizes all the different aspects of the statue in a single picture. Okay, so here's some other techniques. So this low-level abstraction is basically concerned with how objects are presented. And these are just a summary of what I told you before. And high-level abstraction is basically importance driven. So we'll talk a little bit about these things now. Low-level is how things are depicted: silhouettes, contours, pen and ink, stippling, hatching, and all these things. What I showed you before, right? Like basically how the object looks. And high-level abstraction is basically now stripping away certain things and enhancing certain things, in an importance-driven way. Okay, so here are some examples for this. So cutaways, exploded views. Here's a cutaway, exploded views, right? Just taking objects and splitting them apart. Here's another one like this, right? Exploded views. Here's like figuring, like basically culling away surfaces in a way that you can see the inside but still see the outside, right? Ghosting is another one, right? Where you render faces, where you render edges on top, edges of the contours of the object, but you render it on top of the interior. So you get a little bit of an idea what it looks like from the outside, you get a little bit of idea of the outside structure, but you can also see what's inside, right? So here's basically a ghosting effect. You can see the inside of the engine, but you can also see the edges of the engine outside, right? So it's you see both at the same time, right? You can see, basically illustrative rendering effect again here, right? You can see the outside of the skull, but you can also see the inside, the teeth, right, and so on, right? jaw like this. And here the same thing, you can see this tibia here, and then you can also at the same time, you can also see the body. Right? And here's another one, right? This is from a medical atlas, and this is from a volume rendering. Right? Same idea, right? Basically render the interior, but also render the exterior at the same time. So yeah, this is what's called fans, right? Fan is basically taking something and porting it to the outside, right? Showing a particular part of the object and showing it in more detail on the exterior of the object. This is called a fan, right? Something basically a little bit like overview and detail, right? Where you show the detail outside, but you indicate where you come by this fan kind of structure, right? This gray kind of trace. You sort of show the user where it came from, okay? Then, this is basically the same thing a little bit. This is you basically importance rendering, right? Now you basically render things that are important, render them interior, but keep the exterior, or you render it at a different color. It's another one where you split the head, dynamic multi-volumes, or you take the skull and move it up. I don't know who wants to see this, but it looks cool. It sure looks interesting, right? It gives you it's kind of like it gives you an idea what the object looks like, right? Another one is like ray deflectors. It's also an important technique. So instead of, if you want to render something like deform it, you can either take the object and really deform it and then resample it in a new volume, or you can do the inverse, right? Instead of, instead of pulling it out and rendering it with a straight ray like this would basically, if you want to render like this sort of, if you want to take a cube and pull something out of the cube, if you want to make that look happen, right? Either you do it beforehand, like by deforming the volume and then render it with regular ray casting, or you have a ray deflector, basically deform the ray in the opposite way, right? Just instead of a straight way, you have the ray go to the interior, right? It's basically either you can pull this out, or you can do the inverse with a rendering ray. Whatever you do, the same thing happens, right? The same thing happens. Okay, it's just like basically you have to know, okay, in this area I want to pull things out, so in this area I want to pull the ray in. Instead of pulling the object out, I'm pulling the ray in. Same thing will happen. Okay, same thing will happen, because now the ray will go in here, try to render it, shade it, and then it will look like this. Right? Because now the ray has gone outside the object, now it has gone inside the object, and then it will try to render the object there, right? And basically, when it reports the rendering back to the pixel, it will say there was an object, right? And then to do the eye, it will look like this. So you can take a skull and make the nose out, right? Or you can fold things, you can make holes into an object, right? You can take things and then sort of split them apart, right? And see the inside, right? Just by ray deflection. Okay. You can do characteristic rendering. You can basically take an object and map it to a normal object. And whenever something doesn't look quite like the normal object, you emphasize it. Okay, you pull it even more, right? So you compare this nose with this nose, and you realize that this nose is a little bigger. Then when you render it, the nose is even more big, right? It's like just an image space, but so you find a mapping between this and this. You see, oh, this nose is much bigger than this, and whenever you find the nose, you pull it, you warp it out. You can do the same thing also in volume rendering. You can do caricature volume rendering. So here you just need a reference volume, right? You have the reference model, compare whatever you render with this, and you find out there's a lot more volume here, and then you put a ray deflector, make it even bigger. So this you probably know from the Olympics. You just replicate the picture multiple times in terms of the trajectory of the time. Right here, the same thing. You can make, you can render a different style, make it transparent here, or make it opaque here. Give basically the viewer both sides. So this basically exploits symmetry, right? Because heads always look the same left and right, right? So here you can show one side you show transparently and one side you show opaquely, right? So basically exploit the symmetry, and you can see both things at the same time. Okay. So these are, you can also do time rendering, right, by stroke lines. This is like typical, if you want to show like a baseball pitch or something, and then you show like how the hand goes or how someone running. You can show the movement of the person, right? Same thing you can do for scientific volume rendering, right? When you have time varying volumes, you can look at these time varying objects, right? And then you can just render them transparently until you get to the final frame. Or you can connect two things with a stroke line, right? You can do the same thing. You can also sort of simulate this effect, like motion hint effect, like flash photography. So the way this was created, basically the camera was open for a long time, so you could see like as the ball fall, and then you do a final flash photography to render the object, right? And then you sum all of these things together. So you just keep the frame open for a while, and the object comes down, right? And then you do a flash photography, and then you close the shutter. The same thing you can also do with rendering, right? Volume rendering is you basically, render things very faintly, and then you render it with full detail, and then you get this kind of picture. Same thing here. So I want to show you some videos at the very end. Okay, there's some videos I want to show. So this is like, okay. Oh, I actually didn't want to show this. I want to show this video. Open with. So this is importance rendering on the moving, right? So it always changes transparency. Changes transparency as you look at it, right? So it always looks transparent no matter where but it always makes it transparent the way you look at the object. So you have to know where the object is, and then the rays that hit the object, everything else in front of it is basically not rendered. Okay. Here's another one. So here you're basically cut away whenever you look at this particular object, right? No matter where you look for it, you always cut away. And that sort of gives you a little bit of an idea of the surrounding of it, because that changes, and also the shape of the object as you look from different areas, right? But it keeps the sort of the overall context too. Okay.